Hello students, welcome to Educate. Today we are going to continue with chapter number 4 of NCERT Physics class 12. So we are going to start magnetic field due to a current element, Biot-Savart's law. So Biot-Savart law is used to find the magnetic field at any point. Consider a wire of any irregular shape. Suppose this is a wire and here we consider small current element because it carries current. So we take any point here at distance r, so this is point P and this angle is say theta. So we have to find out magnetic field at this point. Suppose this wire carries current I. So it is found that magnetic field due to small current element, this is say dl, this portion, is proportional to here many factors we can take into consideration. The number one, it is proportional to current, it is inversely proportional to distance square, it is proportional to sine theta, now it is also proportional to current element. So these are things, if we combine, what do we get? So we can say dV proportional to I dl sine theta divided by r square, right? Now since there is proportionality sign, we need a constant. So we put a constant here, dV equal to mu naught upon 4 pi times I dl sine theta divided by r square, where mu naught upon 4 pi equal to 10 power minus 7. Now there is question, what is unit of mu naught upon 4 pi? So in order to decide the unit, what we can do? We can just find the unit from here. We need unit of mu naught upon 4 pi. So keeping mu naught 4 pi here, other things I dl r square we can set to this side, sine theta for maximum value we can remove it as 1. So we will get dB times r square divided by I dl. dB is Tesla, means this is magnetic field, this is meter square, I is ampere and dl is length, which is meter. So what is left? 1 meter will cancel out. So you can say Tesla meter ampere minus 1. So Tesla meter ampere minus 1. So that will be the unit. If we write this relation in vector form, then we can take dl as vector and we can introduce unit vector r cap. So which will be vector r divided by modulus r. So if we introduce here this r cap and then we write this value, so vector r will be in numerator, and in that case this r will get multiplied to this and this will become r cube. So our relation in vector form will be dV vector will be equal to mu naught upon 4 pi, then I dl cross r, because sine theta is there, E cross B equal to AB sine theta divided by r cube. And if you want to find out the direction of magnetic field, then find the direction of dl, find the direction of vector r, and then use the formula of cross product, and you can easily evaluate. So we have understood what is Biot-Savart's law. Now one interesting fact we are going to derive here, that is, you know that constant used while calculating Coulomb's force, that was 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. And here we have used constant dB equal to mu naught upon 4 pi I dl sine theta divided by R square. Now we are going to take this constant and this constant, and let's see what result does it give. So what do? We know 1 upon 4 pi epsilon naught equal to 9 into 10 to the power 9, and mu naught upon 4 pi is equal to 10 power minus 7. Sorry, 10 power minus 7. If we write it 4 pi upon mu naught, then it will become 10 power 7. 1 upon 4 pi epsilon naught equal to 9 into 10 power 9, and 4 pi upon epsilon naught equal to 10 power 7. If we multiply these two, 1 upon 4 pi epsilon naught multiplied by 4 pi upon, this is mu naught, sorry, mu naught will be 9 into 10 to the power 9 into 10 to the power 7. 4 pi will cancel out. We will be left with 1 upon mu naught epsilon naught equal to 9 into 10 to the power 16. So we have got 1 upon mu naught epsilon naught as 9 into 10 to the power 16. If we write it as 3 into 10 to the power 8 whole square, is it okay? Yes, it is okay. Now, if you remember, this is c, speed of light in vacuum, 3 into 10 to the power 8. So here c square, 1 upon mu naught epsilon naught equal to c square, or c equal to 1 upon root of mu naught epsilon naught. So you can say speed of light is equal to 1 upon mu naught epsilon naught with square root. Now suppose in exam sometimes this question comes that find the dimension of mu naught epsilon naught or root of mu naught epsilon naught. Then you can easily evaluate. Suppose you want to find out dimension of mu naught epsilon naught. So what will you do? Take it in numerator. So dimension of 1 upon c square. C is the speed of light. Speed means distance upon time. C will be L upon T. So T upon L. So this will become 1 upon L square upon T square, or T square upon L square. So which will give L power minus 2 T square. So this is how you can find the dimension. So this is one important question, and you should know. Here we are going to see one question based on Biot-Savart's law. Here in our question, current element dl equal to delta x I cap, it means in this direction, is placed at the origin and carries a large current I equal to 10 ampere. What is the magnetic field on the y-axis at a distance of 0.5 meter? Take delta x equal to 1 centimeter. So recently we have studied that dB equal to mu naught upon 4 pi I dl sine theta divided by r square. So here in our question, information is given I is 10 ampere and dl sorry, dl will be equal to, from here, dl equal to delta x, and delta x is 1 centimeters, so we can write in place, if we put the values, this is 10 power minus 7, I is 10 ampere, dl can be taken as delta x is so 0.01, and if you want to write its magnitude only, then it's okay, otherwise you can take in terms of vector also. So later on we will see, for getting the direction of the field we can use vector form, but here just put the values. So I dl sin theta is 1 because perpendicular, this y-axis, this is x-axis, divided by separation square, distance is 0.5 square. So from here you can get the value of magnetic field in Tesla. Now in order to find the direction of magnetic field, what will you do? So here you can use the concept that here you can use vector concept like A cross B gives AB times sin theta. So in place of that you can write the dimension here, what quantities are being cross multiplied. So you have taken I dl, and then if you write it in vector form, so just consider dl. So dl will be along the x-axis, so just take I cap and the vector r. So you are taking in this direction y-axis, so just write j cap. So I cross j, from here if you remember the rule, if you write here I, here j, here k, so you will get k cap. So field will be perpendicular upward or along z-axis. Here same thing is explained if you observe the solution. So you will notice values are put, and after that we have got b equal to 4 to the power minus 8, and the direction of the field is in z direction, and the rule that I told you. So we just write I cross j, I cap cross j cap, that will give k cap. So that is simple. Now we are going to see another question. Here in this concept also we are going to make use of Biot-Savart's law, and then we will derive the result for a particular situation like at the center of the ring, etc. First we will consider the point on the axis of the ring. There we will find the magnetic field, and we can imagine that here in the figure one turn is given. It can have n turns, then what will be the net magnetic field at this point, and then it's a generalization can be done. So if you wish to read it, so let's read the question, although it is simple. Here figure depicts a circular loop carrying a steady current I. So there is current in it, I current. Here we are considering small current elements dl and here dl diametrically opposite, and due to them at this point we will see the magnetic field. And then finally we will sum up by using integration. So the loop is placed in YZ plane with its center at the origin and has a radius r. Radius of loop is r, and distance of the point P from center of the loop is x, and that distance is r as shown in the figure. Now we wish to calculate the magnetic field at the point P on this axis. Let x be the distance of P from the center O of the loop. Consider a conducting element dl here or here of the loop. This is shown in the figure. Now the magnitude dB of the magnetic field due to dl is given by using Biot-Savart law. As you know, dB equal to mu naught upon 4 pi I dl cross r upon r cube. This is in vector form. Here if you apply Pythagoras theorem, you will get r square equal to capital R square plus x square. Same thing is written here. Further, any element of the loop will be perpendicular to the displacement vector from the element to the axial point. For example, the element dl in the figure is in yz plane, whereas the displacement vector r is dl is in axial point in the xy plane, obviously. So here theta will be 90 degree. In that case, ideal sine theta will give just ideal. So we can write the relation here. We are taking original form ideal sine theta divided by r square times mu naught upon 4 pi. So this is basic relation dB equal to mu naught upon 4 pi ideal divided by x square plus r square. Value is not put here, keep in mind. This is not in vector form, original form, this one. dB equal to mu naught I dl upon r square. So we are taking this. Okay, so we have got this relation mu naught upon 4 pi I dl time x square plus r square. Now here we will consider different components. So in previous figure, if you observe, you will see that cos theta component will contribute to the magnetic field and sin theta component will cancel out. So in this figure, what will happen? So perpendicular component is shown like this, and this is x component. So cos theta component will add up and sin theta component will cancel out. So here, when we find total magnetic field, in that case we will find sum of all cos theta components. And what would be the cos theta here? So cos theta can be found by x upon r, and in that case r equal to, again same thing, r square equal to x square plus r square can be applied. So that value we are going to put here, and then we will integrate the value to get total magnetic field due to this ring. So here the same thing is explained. So cos theta will be r divided by x square plus r square half. So in that case, if we put total value, so let's write it here. dB will be mu naught I dl divided by 4 pi times r square. R square is x square plus capital R square, and times cos theta. And cos theta, from previous figure, if you observe, theta is not shown in the diagram, but cos theta will be taken from radius, will be the base in that case, and that distance hypotenuse will be considered. So in that case, cos theta will be taken like this. This will be r, and this will be small r, and then this will be x. So cos theta will be based upon hypotenuse. So r upon capital R, sorry, capital R upon small r we can write. So mu naught I dl divided by 4 pi x square plus capital R square into, this will become r upon, this will be square root of x square plus r square. So if we further evaluate, so what do we get? Mu naught I dl times r divided by 4 pi x square plus r square whole power 3 by 2. So the same thing is written here. Now we need its total value. So total value can be found, because in this case we have considered only current element dl here. Similarly, other points will be there, and due to these current elements we are finding, we have taken cos theta component. Now suppose we want to find out full contribution of the ring. In that case we can integrate it. the same relation can be integrated. So what would be the limit? Limit will be total length of the ring. So we can say 0 to 2 pi r, we can take the limit. So if we want to find out b, in that case we write 0 to 2 pi r and then we integrate this dv. So if we put the value, so b will be equal to mu naught divided by 2 pi, sorry, mu naught upon 4 pi times, let's write it once again. So b will be equal to integration 0 to 2 pi capital R, and then we put value of dv, so 0 to 2 pi r, and this is mu naught upon 4 pi, then I dl r, so here right here dl divided by r square, where r square can be written as, here its value is small, it was x square plus capital R square whole power 3 by 2. So here what is integrable term? Integrable term is just dl. So integration of dx, if you remember, it becomes x. So integration dl will become L, and then we will put the limits. So we will get b equal to mu dot upon 4 pi, then I r times dl will become L, limits 0 to 2 pi r whole divided by x square plus capital R square whole power 3 by 2. Now we put here limit, so we will get 2 pi r here. So it will become mu naught upon 4 pi I r into 2 pi r divided by x square plus r square whole power 3 by 2. Now this 2 pi will cancel out and I r square will be left. So our result will be like this. And in terms of vector, the result will be along x-axis. So bx I cap, same value as I have shown there. So this will come out to be this much, mu naught I r square divided by twice of x square plus r square 3 by 2. Now special case. So as you have seen, this point was at x distance from center of the ring. Now if we keep x equal to 0, then our value of magnetic field will be limited to the center of the ring. So magnetic field at the center of the ring will become, here this term will become 0. So r square 3 by 2, 2 will cancel out, r cube will be left, and in numerator there is r square, so r square divided by r cube, so r will be the result. So we can say magnetic field at the center of the ring will be b0 equal to mu naught I divided by 2r and then I cap. So I think you have understood the concept. Now the magnetic field lines are shown due to the ring, as you have already studied in lower level also how to represent the magnetic field lines if there is current carrying loop. So I'm not going to explain it, that's your work. Now further, let's see. Here you are given this is semi-circular arc. Current is going like this. This is another semi-circular arc. Current is going like this. You have to find out the magnetic field at its center. What is rule? Recently you have seen that B at the center of coil is how much? B equal to mu naught I divided by 2r. It was like this. So same concept will apply here. but since it is half ring, right, only half portion is there, so this value will get halved. So if you make it half, then what will it be? So mu naught I divided by 4r it will become. So here in first case, if you observe, so if value of current is given, radius is given, so you can easily evaluate. The same will be true here. But if you want to find out what is the direction of magnetic field, keep in mind that these portions will have no contribution to the magnetic field here at the center. Even here, this portion and this portion will not contribute to magnetic field at this point, because region is given here, region you will understand. So our concern is to find out the direction of magnetic field at this point. What is rule? Rule is very simple. If this is wire, so at the right of the wire, if current is going upward, at the right of the wire, field will be perpendicular down, and at the left of the wire, field will be perpendicular upward. If you consider that way, so here this will be left of the wire. If you are here, wire is like this. If you are here, so field will be perpendicular, as I told you. If direction of current is this, so to the left of the wire, field will be perpendicular up. So at this point, field will be perpendicular up, and at this point, field will be perpendicular down. The same thing is true here. If current is here, so you are considering current like this. So to the right of the wire, so if you consider here, so this is a point on the right of the wire. So here field will be perpendicular down, and here field will be perpendicular up. So I think you have understood. The same thing is shown here, and explanation is given that you can easily understand. Now let's take another example. The example says, consider a tightly wound 100 turn coil of radius 10 cm carrying current of 1 ampere. What is the magnitude of the magnetic field at the center of the coil? We have recently derived the result, if you remember, that B at the center is mu naught I divided by 2r, where r is the radius of the ring. Now, if ring contains n turns, then here the formula will get multiplied by n, and no more changes will take place. So same thing in this question, you will observe. Consider a tightly wound 100 turn coil. So value of capital N is given 100, and the radius is given as 10 centimeter, and current is given as 1 ampere. What is the magnitude of the magnetic field at the center of the coil? So you can apply that formula, that is mu naught Ni divided by 2Ir. Put the values, you will get 6.28 into 10 power minus 4 Tesla. I think you have understood. It's simple question. Now let's consider Ampere circuital law. Ampere circuital law is used to find magnetic field due to current element. Here, if you read it, there is an alternative and appealing way in which the Biot-Savart law may be expressed. Ampere circuital law considers an open surface with a boundary. Figure is shown. Now, the surface has current passing through it. We consider the boundary to be made up of number of small line elements. Consider one such element of length dl we can take, and then we take the value of the tangential component of the magnetic field bt at this element and multiply it by the length of that element dl. So bt dl equal to b dot dl. All such products are added together. We consider the limit as the length of elements gets smaller and their number gets larger. The sum then tends to an integral. You know, when summation of very small quantities is done, in that case it becomes integral. So the basic point when we use this symbol sigma, and if Suppose we have to evaluate sigma x. Here x must have certain measurable length, but when x is very small, in that case sigma x will tend to integral x. Or suppose here we write sigma dx, so integral dx. So this is the point. The same thing they are saying, that we are going to sum up small elements, and ultimately integration b dot dl means product of b magnetic field and current element dl gives mu naught I. And if dl is known, from here we can derive important result. Integration, this is closed integral, means loop should be closed, and b dot dl equal to mu naught I. Here if theta between the two is 0 degree, then b dl integration equal to mu naught I, and dl integration dl will give length b into l and equal to mu naught I. It depends. If suppose this is wire of length l, then it will remain like this. If it is a loop of radius r, then this L will become 2 pi r. So it depends on context, and you can make use, then different results you will get. The same thing is explained here. For several applications, a much simplified version of that proves sufficient. We shall assume that in such cases it is possible to choose the loop called Amperian loop. Keep in mind the loop that we considered that was carrying current. So that is called Amperian loop. This is an important point. B is tangential to the loop and it is non-zero. Constant B is normal to the loop. B vanishes. So three situations are there. If there will be no current, then definitely B will not be there. So this is the result that we have derived. Now here when there is a system with a symmetry such as for a straight infinite current carrying wire, we will see in another case, the Ampere's law enables an easy evaluation of the magnetic field, much the same way Gauss law helps in determination of the electric field. This is exhibited in the example 4.8 that we will see. The boundary of the loop chosen is a circle and magnetic field is tangential to the circumference of the circle. The law gives for the left hand side of the equation B into 2 pi r. As I told you, when you take circular portion, in that case L will become 2 pi r. So in that case we will write B equal to mu naught I divided by 2 pi r. The above results for infinite wire is interesting for several points of view. So here, suppose this is a wire carrying current and its length is infinite. In that case, at any point at distance r, its magnetic field will be given by mu naught I divided by 2 pi r. So that is the interesting fact. Here its derivation is not given, so I'm not going to derive. Now here some important results are given, like cylindrical symmetry, etc. So that you can read, and if difficulty comes, I will explain you further. Now here there is one very important question. This is frequently asked in board exam, in school tests, etc. So read it carefully. Let's try to understand what is there. So figures 4.1, so this figure shows a long straight wire of circular cross section, radius A, its radius is A, carrying steady current I. The current I is uniformly distributed across this cross section. Generally what happens? Current lies on the surface. Here the strange point that has been inserted here, that current is uniformly distributed throughout its volume. So if this is wire and its this area of cross section is, say here this is say R, So area of cross section will be pi r square. So pi r square cross section will carry current I. But suppose you just consider half of it. Suppose area you make pi r square by 4. Then current will also decrease correspondingly. So you can apply unitary rule that we are going to discuss soon. So here question says, shows a long straight wire of circular cross section radius A carrying steady current I. The current I is uniformly distributed across this section, cross section. Calculate the magnetic field in the region when R is less than A. R is less than A means what? This total is A. So inside, and R is greater than A means outside. So when we consider inside any point, in that case current will reduce because current is uniformly distributed throughout the volume. But if we take this outer circle, in that case current will remain same. So two situations we will deal, and then we are going to draw the graph for the same. So let's proceed. Here, first case. First case means we are considering the situation. This is wire. So this is A, and now we are taking any point here. Small circle. Suppose this is R. Here situation we are dealing with is R is less than A. So we have to find out what is current in this circular region. If I current is for this circular region of radius A, so for that, first of all, since we need BL equal to what the formula? Mu naught I. So here what will be L? L will be length of the loop that we are considering. So L will be 2 pi r. Right. So you will write B into 2 pi r equal to mu naught I. But you can't take it I. Here I will be something different. So what is I? Because as I told you, here area pi a square. Let's make it clear. Area pi a square contains current I, right? So unit area will contain current I upon pi a square. Then here pi r square, pi small r square area will contain current I upon pi a square times pi r square. So pi will cancel out. We will get I upon a square times r square. So this will be value of I dash. So here we will write this B into 2 pi r equal to mu naught times this value I upon a r square, I upon a square into r square. So here one r will cancel out and other things are constants. So we can say B proportional to r. So inside we have got B proportional to r. If we plot the graph for inside, so it will be straight line till we reach to the surface. When small r equal to capital, small r equal to small a, in that after that point the situation will change, the graph will change. So we have analyzed till point r equal to a, right? So this is first thing, means here point is taken here, or you can take here till here, any point you can take inside. So situation will remain same, or you can say B will be directly proportional to radius. Now we are going to consider a point that lies beyond the wire. So in that case what will happen? and then what will be the graph. So if we go beyond, in that case the situation will change. So when small r is greater than a, then what will be the current enclosed? Wire is like this, radius is a, and now we are considering this type circle, radius r, right? In this case formula will remain same. So this time we will get b times 2 pi r equal to mu naught times current enclosed. Here the whole current is enclosed because current is uniformly distributed and our circle lies outside the wire. So entire wire is within the imperial loop. So it will be mu naught I. From here B proportional to 1 upon R. So outside, this is the situation. So we have got inside B proportional to R and outside B inversely proportional to R. So if we plot the graph combined way, so we will reach till here where B proportional to R, and after that graph will be like this. Here B is inversely proportional. So you have understood the concept. Here we have considered the Biot law, and then we applied it to get the magnetic field at different points of the wire, and the wire was carrying current I, but that current was uniformly distributed throughout its volume. So today I will stop here. In next lecture we will continue with the solenoid and other important aspects like force between two wires and other related facts. Thank you for watching. Team Educate.